Who's ready for the last dad joke of the school year? Well, I guess I can continue telling them. Well, let me put it this way then. Last dad joke that will be recorded this year. So, I had another dream last night. A lot of weird dreams.
What was it?
Well, I had a dream that I was a muffler. I'll tell you, I just woke up totally exhausted.
That was a really good movie.
Thank you. Gotta go out strong. So the last two worksheets then are simple harmonic motion worksheets 4 and 5. And these take the same concepts that we talked about in the last video with force and acceleration and velocity and displacement, but now we add numbers to these things. And I'll just kind of show you how to do that. These equations that we'll be dealing with are all on your formula sheet in the simple harmonic motion box. So the first one I just want to point out is spring force. And spring force is equal to negative kx. K, if you remember, is a spring constant. The bigger the k value, the more strong that spring is going to be. And x is just your displacement, your distance from the equilibrium point. If you multiply those two values, you have your spring force. As you'd expect, the further the displacement from the 0 point, the bigger, bless you, that spring force is going to be. Now, the reason it's negative is simply because, bless you again, your displacement is always going to be opposite the direction that the force is applied in. So if you think about it like this, if we say letter A is the negative direction, or let's do it like this. E is the positive direction. And let's just say that our mass is all the way at E over here in the positive direction. Well, if to the right is positive, then what direction is the mass being pulled? It's being pulled to the left in the negative direction. So because the displacement and the direction of the force are always in opposition, our spring force will then always be a negative value. So that one's pretty straightforward. Another one is this guy here. Looks pretty similar to the pendulum equation. Period is equal to 2 pi times the square root of m over k. And this is just another equation where you can calculate the period of oscillation as the spring goes back and forth one time. So one period for this would be like if you start at letter A, it goes back and then it comes back to letter A right there. That would be one period of oscillation. Or you could start at E, and then if it goes down and then comes back to letter E, that would be your period. The other equation that we just have to kind of be a little bit aware of, it's one that we've dealt with already in the energy section. Because we're dealing with springs now, remember that springs have a certain amount of potential energy. So remember that spring potential energy is 1/2 kx squared. And again, that k is your spring constant, x is your distance from the 0 point. And the last equation, this one is probably the least important, but I am going to do an example that has kinetic energy in it. That's 1/2 mv squared. So those are the main equations we're going to be looking at, primarily these top 3. So let's take a quick look at what's going to be going on for our oscillating mass to the left there. So what we're going to do is we're going to actually put numbers to these values, more specifically the spring potential energy. So as this mass oscillates back and forth, its spring potential energy grows and dissipates. Its maximum spring potential energy would be located at points A and point E as the spring is compressed and it's got that spring potential energy, and when the mass is all the way over here, and now it's stretched to its maximum distance, then it also has a good amount of spring potential energy. So in order to figure out how this is all going to go, I just kind of want to assign some numbers to these things instead of actually running calculations. We've dealt with these equations long enough. We don't need to have the busy work of just doing simple math with them. But let's say that we have a whole bunch of numbers here, and maybe it gives us a distance, and it gives us a spring constant K, and we're able to figure out from that information that the spring potential energy at letter A is equal to 5 joules. So that's our spring potential energy at letter A. Now that also would mean that the spring potential energy at letter E would also be 5 joules. At letter C, it's going to be nothing, because at letter C, that's the equilibrium point. So that spring is not really pulling or pushing at that area. So we've got 0 joules right there. And let's just say for letters B and D, we calculate a spring potential energy equal to 3 joules at those two positions. So this is the information that we have. And perhaps the question then is, what is your kinetic energy at each of these positions? So let's just see if we can figure that out. You can, even if it does not give you a velocity. And you can figure it out if it does not give you a mass. Who would have thought that? Kinetic energy is 1/2 mv squared. If we know the spring potential energy for these positions, that's all we need to figure out what the kinetic energy is at these different areas. So let me just quick show you how then. Now at letter A and E, these are the positions where your total energy is going to be fully and completely spring potential, because your maximum compression here and your maximum distance here, all of your energy is in spring potential form at those locations. So at letters A and E, that would mean that your kinetic energy would be equal to nothing, because all your energy is spring potential at those locations. Now letter C is a little bit different, because here you have no spring potential energy. But if we know this whole system contains 5 joules of energy, that means at letter C, when there's no energy for spring potential, that means all of that spring potential is now transferred to kinetic. So 5 joules would be your kinetic energy at letter C. All of that spring potential energy that you had at A and E is now transferred to kinetic energy at letter C there, which is 5. You'd be moving your fastest at this position. And finally, letters B and D. These are the ones that are just going to take a little bit more thinking. Now, again, at its maximum, letters E and letter A, you've got 5 joules of energy. It's all spring potential, but 5 joules of energy is the grand total amount of energy that this system has as it oscillates back and forth. And as it oscillates, that energy is distributed, between spring potential energy, and now it's turning into kinetic energy, more and more kinetic energy, and now you've got maximum kinetic, and then from here on out, the kinetic decreases, getting more and more spring potential, and now you've got your maximum spring potential over there. But if you add everything together, you've got 5 joules of energy between those two energy forms this entire time. So, letter B, if we've got 3 joules of spring potential energy, how many joules of kinetic do we have? 2, exactly. So they have to add up to 5. And of course, same thing for letter D. And that's really all you need in order to figure out worksheet number 4. Again, the main thing with this is that you keep the same amount of energy as this block oscillates. That energy is changing, from kinetic to spring potential, but overall your grand total is going to be 5 no matter what your position is. And the last thing I want to talk about just briefly for worksheet number 5, it deals with amplitude. If you're talking about amplitude on this example, your maximum amplitude would be at letter A, that would be the negative direction, and E would be the positive direction. So at those two spots, your mass is at amplitude. That's the maximum displacement. That's all that amplitude really means. Frequency we've dealt with in the past in the waves section, along with period, and that relationship is in that box. So it's just a matter of taking note of that. And it also deals a little bit with this equation right here. So, like, one of the things it talks about is how is the period of your pendulum going to change if you would say change its mass. And of course, if you change its mass, if you make it bigger or smaller, that's going to change this value here, which will change your overall period. So yeah, you would just go through the reasoning with that, just like we did for the pendulum equation. That looks very similar. And that about does it. Questions on anything? Okay. Well, that's the end of physics.